Hey guys, my name is IBM and today I'm taking you to lesson 2 of Waves. My students told me I should make these lessons a little bit shorter so that they have enough break after every lesson. So I've decided to reduce the length of these lessons. So do not forget um, to watch the solved past paper questions. They will give you more confidence with this AS physics syllabus. I've recorded all the topics and they're in playlists which you can check out to practice and gain more confidence. And if you're my student, I'm very certain most of these topics I'll not teach them in class or I'll not teach them in details because I have recorded them and I want you to take the initiative to use your time to at least go through them at your free time. The reason as why I record these lessons is because you can always revisit. You can always revisit to listen to what I actually said about a certain concept. So let's go to Waves lesson 2. So in lesson 2, we shall basically talk about three major areas. One, we shall talk about the graphical representation of waves that you mentioned in IGCSE. It is going to be the same representation, of course. Number 2, I think we shall talk about a wavefront. We shall talk about a wavefront. And number 3, we shall talk about the general wave equation, which you mentioned in IGCSE. And I think that will be enough for lesson 2. Then we shall see more details in lesson 3. Okay, so let us start our lesson 2. Like I said, lesson 2, we shall talk about graphical representations. So let's start with the graphical representation of a wave. I think the graphical representation of a wave you mentioned in IGCSE is still valid even at this level. In IGCSE, you represented a wave as a displacement distance graph, and some of the terms you mentioned might have included the following. You might have talked about the amplitude, which you called the maximum displacement of a particle from equilibrium position. That's what you call the amplitude. The maximum displacement of a particle on a wave from the equilibrium position, that is the amplitude. Remember, displacement is a vector quantity and therefore it is measured in a specified direction. So the displacement of a wave, or the displacement, is the distance moved by a particle in a specified direction from its rest position. And the displacement being a vector quantity, it can either be positive or negative. So from your representation that you used in IGCSE, any maximum displacement from the horizontal line to the highest point, which you call the crest in IGCSE, or represent a distance from the equilibrium position, which is the horizontal line, to the lowest point, which you call the trough in IGCSE, that is going to be the amplitude. Is actually the maximum displacement of a particle on a wave from the equilibrium position. For a transverse wave, remember the particles are vibrating perpendicular to the direction of propagation of the wave. And for a longitudinal wave, the particles are vibrating parallel to the direction of propagation of the wave. But all of them, in all cases, they all had an equilibrium position, or the central position, or the point where the displacement was zero. So the amplitude is measured from that point where the displacement is zero. So normally for a transverse wave, we shall represent like this, and the amplitude will be the maximum displacement from equilibrium position in a particular direction. And of course, we also have the distance between one peak and the next peak, which we call the wavelength lambda, or the distance between a trough and a trough, which we call the wavelength, or the distance between two corresponding points, such as this point here and this point here. These are corresponding points, as we shall see later on. So this distance here, this length here, between two points, these points are vibrating in the same direction. We shall later on say they are in phase. These points have reached the same point in their motion. So they are at the same displacement, they are vibrating the same direction at the same time. The distance between two such points, which are vibrating the same direction at the same time, and they have reached the same displacement in their motion, or in their vibration, or in their cycle. Such a distance is also called wavelength. If the wave is longitudinal, we represent the wavelength as the distance between a point where particles are close to each other, that is high particle density, the distance between two successive positions where we have high particle density, that is what we call the wavelength. And in one of the lessons, or in lesson 1, I think we mentioned that the compressions correspond to the crests and the rarefactions correspond to the trough. So the displacement distance graph, which is equivalent to the displacement distance graph, is also equivalent to uh, the displacement distance graph for a transverse wave is also equivalent to the displacement distance graph for a longitudinal wave. So we can represent both longitudinal waves or transverse waves using just the same displacement distance graph. But remember, the maximum displacement from equilibrium position is going to be called the amplitude, and the displacement is the distance moved by a particle in a specified direction, as we saw in a unit called kinematics. Remembering that distance is a vector quantity, so it should have both the negative and positive parts of this cycle, or of this representation. So do not forget, we have talked about wavelength as the distance or the shortest distance between two adjacent particles. Those are points that are vibrating in phase. Now, when I say the shortest distance and then I say two adjacent particles, I'm almost repeating myself, because when I say two adjacent particles that are vibrating in phase, it is equivalent to the shortest distance between two particles that are in phase. So we don't skip a particle, just consider one particle which is in phase with the next particle. In phase, we shall explain what we mean by phase later on. Or we can define a wavelength as the shortest distance between any two adjacent identical points on the wave. Identical is also equivalent to them being one in phase. They have reached the same point in their cycle and they are vibrating the same direction at the same time. So they are going to be considered to be identical. It can also be defined as the distance moved by the wavefront. I said in lesson 2 we are going to talk about a wavefront. So the distance moved by the wavefront during one oscillation of the cycle of the wave is going to be called um, the wavelength. So the wavefront, the distance which one wavefront moves in a complete cycle, the distance one wavelength makes in a complete cycle is what we call the wavelength. The easiest definition for wavelength that my students always write is the distance between two adjacent wavefronts. We are going to see what we mean by wavefront later on, but the distance between two adjacent wavefronts is going to be called um, the wavelength. Of course, we have also defined it as the distance between adjacent crests, the distance between adjacent troughs, the distance between successive crests, the distance between successive troughs, the distance between adjacent compressions, the distance between adjacent rarefactions, and so on and so forth. So all that is defining a wavefront. So as applied to longitudinal waves, a wavelength is the distance between two adjacent compressions or adjacent rarefactions. Because longitudinal waves are made up of compressions and rarefactions, then we can also define wavelength as the distance between two adjacent compressions and rarefactions. We can try to demonstrate this in more details. So I want you to recall and also note that particles are said to be in phase if they are at the same stage of their motion. That is, they have reached the same displacement from the equilibrium position and they are traveling in the same direction. So if particles are vibrating upwards, two adjacent particles should be vibrating upwards and they should have reached the same stage of their motion. In other words, they have reached the same displacement from the equilibrium position and vibrating in the same direction. We shall say those particles are in phase. That's why I say the distance between two adjacent particles that are in phase. Also, I want you to note that the displacement of a longitudinal waves is represented in terms of compressions and rarefactions along the direction of travel, where we know that where particles are very close to each other, we have what we call high particle density. And I said the pressure there is relatively high, or the air pressure there would be high if it is a sound wave due to vibration of air molecules or air particles, and the air pressure there is going to be high. And we say that the distance between two adjacent compressions is also called the wavelength. And of course, the distance between two adjacent compressions, of course, measuring this from the center, will still be the wavelength. And we say that the crests for a transverse wave would correspond to the high pressure point for a longitudinal wave, where particles are under maximum pressure or they are under high pressure. So do not forget that the crests of a transverse wave correspond with the compressions. So the crest corresponds with the compressions of a longitudinal wave, and the troughs correspond with the rarefactions of the longitudinal wave, as I illustrated in this diagram here. But do not forget that the maximum displacement from equilibrium position is the amplitude, and the distance between adjacent crests is the wavelength, or the distance between adjacent compressions is the wavelength, or the distance between adjacent rarefactions is the wavelength, or the distance between two adjacent particles that are in phase. For example, a particle here is in phase with the particle here, and the reason is because the particle here is most likely going to be vibrating downwards, and the particle here is also vibrating downwards. These particles are all passing through equilibrium and they are vibrating in the same direction, so we say the particles, this particle A and B, are going to be said to be in phase. We shall understand phase in more details later on. We can also, by the way, represent waves in terms of displacement against time. You must also have done this in IGCSE. You represented waves in terms of displacement against time graphs. In this case, we were able to define the time period. So since now we have displacement against time, we can't say that this is this wavelength, not at all, because wavelength is a length, it's a distance. This is against displacement against time, so it means from one peak to another peak we have time for one cycle, which can be the same as this time here, because one cycle stops here, which can be the same as this time here, because this is one complete cycle. So a half of a cycle plus half of a cycle, we have a complete cycle. So the time for one complete cycle is going to be called the period. The time for one complete cycle is what we are going to call the period. The time taken for a wave to make one complete oscillation, one complete vibration, one complete cycle is what we are going to call the period. I think you called it a period in IGCSE. So period of a wave is the time taken for the particle in a wave to complete one cycle or vibration, one vibration or one cycle. It is the time taken by a wave to travel through one wavelength. Remember, wavelength could also be called the distance covered by a wavefront in one cycle. Now we are saying the time taken by a wave to travel through one wavelength, because one wavelength is one cycle. It can also be called a period. The time taken by a wave to travel through one wavelength, that is a period. Period meaning being time, the SI units are still going to be seconds, as we know the units for time. Then from period, of course, we know from IGCSE that 1 over frequency is going to be equal to the period. So we also need to define frequency. And you define frequency as the number of complete cycles, or the number of complete vibrations, or the number of oscillations of a wave per unit time. Because the frequency of a wave depends on the source, we would best define frequency as the number of complete cycles or vibrations or oscillations of a wave source that passes a given point per unit time. So the number of complete cycles of the source per unit time, because the frequency of a wave depends on its source. If a source makes more vibrations or more cycles per unit time, it means the wave will also have more oscillations or more cycles per unit time. So frequency is the number of complete cycles or number of complete oscillations of the wave source per unit time. We can also call it the number of wavelengths that passes a fixed point per unit time. For example, here I have 2.5 cycles. So I would say the frequency is 2.5 cycles. The number of complete, that is in a given time t. So the number of complete wavelengths, because each wavelength is a full cycle, the number of complete wavelengths per unit time is going to be called the frequency. Of course, the SI unit for frequency is going to be the hertz that you mentioned in IGCSE, the hertz. And since frequency is the reciprocal of the period, it means the unit hertz is the same as the unit per second. The unit hertz is going to be the same as the unit per second because frequency is equal to 1 over t that you mentioned in IGCSE. Okay, so that is the graphical representation of a wave, and I think this is IGCSE knowledge. Let's also talk about under the wavefront, which you never mentioned in IGCSE. So what do we mean by a wavefront? So a wavefront, maybe I don't have enough space, but so let me first sketch something, a wave here, before I explain what I mean by a wavefront. So let me sketch the side view of a wave, and I'm going to modify this into 3 dimensions. So when you look at what I've just sketched here, you get an impression as if this is a wave. So I have drawn a wave in 3 dimensions. When you view it from this side, you'll just see this line here. And what you would see would be a crest and a trough, a crest and a trough, a crest and a trough, and so on and so forth. But when you view the wave from above, if view is from above, you may see lines like this one here. You may see lines here and maybe even lines on in the valleys. You see these lines here. So if I consider a particle here and a particle here on the top of this, both of these particles A and B are on the crest. They have reached the maximum displacement. And if they are on the crest, we could consider these particles to be maybe vibrating because they have formed a crest, they may be vibrating vertically downwards. So these particles have reached the highest point of their motion. I mean, of their cycle. They have reached the highest stage of their cycle at the same time, and they are vibrating in the same direction. So we say that the particle A and B are in phase. So if I draw a line through these particles which are vibrating in phase, then the line through these particles, which is of course an imaginary line, the line through these particles which are vibrating in phase is what we call a wave front. So a wave front is simply a line or any section taken through an advancing wave in which all particles are vibrating in phase. So particles here are in phase. So if I draw a line through these particles, I form what we call a wavefront. Particles here are also in phase. If I draw a line through these particles, I form what we call a wavefront. An observer viewing the wave from the top will just see horizontal lines instead of the wave that we see from this side, from the side view this side. So any line or section taken through an advancing wave in which all particles are in phase is what we call a wavefront. So you should be able to define what we mean by a wavefront. A line or section taken through an advancing wave in which all particles vibrate in phase or are in phase. That's what we call a wavefront. Okay, so I'll just first of all erase this. So any line or section taken through an advancing wave in which all particles are in phase is what we are going to call a wavefront. It is actually imaginary, so it is not a real line. So it is an imaginary line which joins the set of particles that are in phase. We now know what we mean by phase, even though we shall come back to phase and phase difference later on. Particles are said to be in phase if they have reached the same stage of their motion and they are vibrating in the same direction. They have reached the same displacement from equilibrium position and they are vibrating in the same direction. They are therefore said to be in phase. So remember that particles are in phase if they are at the same stage of their motion at the same time and they are moving in the same direction. That's what qualifies particles to be in phase. And the direction of travel of the wave is at right angles to the wavefront. The direction of travel of the wave is at right angles to the wavefront. That is what we have seen with the transverse wave. Along a wavefront, every particle transmitting the wave is at the same distance from the source of the wave and is in the same state of disturbance, as we are going to demonstrate this with animations. So along a wavefront, every particle transmitting the wave or the wave energy is going to be the same distance from the source of the wave and is in the same state of disturbing. That is on the same wavefront. For the same wavefront, every particle transmitting the wave is at the same distance from the source, and it will also be at the same or in the same state of disturbance like the others. There are going to be two categories or forms of wavefronts. We shall see that what we call circular wavefronts in form of a circle, and we shall also see plane wavefronts in form of straight lines or just parallel planes. So when we talk about circular wavefronts, these ones consist of wavefronts that are concentric circles. Circular, they are concentric circles with the source of the wave at the center. Those are circular wavefronts. And a circular wavefront can easily be demonstrated at home. You can just drop a circular object into a basin of water or something containing water. So a circular wavefront can be obtained when a surface of still water is disturbed by a round object such as a marble or a stone. You'll see circular wavefronts being formed. If we want plane wavefronts, because plane means a straight, plane wavefronts are wavefronts which are parallel. That's why we call them plane. They are parallel to each other. Such a wavefront can be obtained when the surface of water is disturbed by a plane object, such as a ruler. If you drop a straight stick horizontally onto the surface of water, you're most likely going to visualize or to see a plane wavefronts. So what I've been just describing is here. Circular wavefronts, for them, they are circular in nature. They are concentric circles with the source of these waves being at the center. When you throw a stone into the water, you will see such concentric circles. So this is a wavefront, this is a wavefront, this is a wavefront. All particles at this line or at this concentric circle here are the same distance from the source and they are in the same state of disturbance. Then if you drop a straight object such as a ruler horizontal onto the water surface, you'll see a wavefronts which are of this nature. These are plane wavefronts or straight wavefronts. However, I want you not to forget that the distance between these successive wavefronts or the distance between two adjacent wavefronts still remains a wavelength. The distance between two adjacent wavefronts still remains wavelength. So this distance is still wavelength. the distance between two adjacent wavefronts is still wavelength, so that one should become part of U. To animate these wavefronts, I decided to use a few animations that I obtained. So you can notice when I drop an object at this center here, I come up with what we call circular wavefronts. And at every wavefront, the particles are the same distance from the source. That's what we mean by circular wavefronts. If I drop a horizontal stick, or I drop a straight stick or straight ruler horizontally onto the water surface, these are the wavefronts that I see. They are plane wavefronts. And if you view a water wave from the sides, you may see something like this. And if you view it from the top, you may see horizontal lines which are going to be called plane wavefronts. So these are what we call wavefronts. Now that we know what a wavefront is, as a section or end line through an advancing wave in which all particles are vibrating in phase, then we should talk about the relationship between speed of a wave, frequency of a wave, period, and wavelength. In other words, the general wave equation, which we mentioned in IGCSE. So we are going to consider a source of waves that produces waves of frequency f. So the frequency is going to be f. Remember, frequency is the number of complete oscillations or number of complete cycles per unit time. And wavelength, lambda, which is the distance between two successive or adjacent wavefronts, or the distance traveled by a complete wavelength, the distance traveled by a wavefront in one complete cycle, that is going to be called the wavelength. So let's assume that a source makes one oscillation, that is one complete cycle. So when a source makes one oscillation or one complete cycle, it means the wave travels forward by a distance of one wavelength. So one cycle is equal to one complete wavelength. So if we say the source makes one cycle, it means the wave which has been generated travels forward by one cycle. Then if we have more cycles, let's say we have f cycles, if f oscillations are made per second, because remember wave frequency is the number of oscillations made per unit time. Let the unit time here be 1 second. So if one oscillation, if the source makes one oscillation, the wave moves forward by a distance of one wavelength. Let's say if it makes f oscillations in 1 second, what is therefore the total distance made? Remember, oscillations, frequency f is the number of oscillations per unit time, and each oscillation moves the wave forward by a distance of one wavelength. So it means the total distance moved by the wave in 1 second is going to be the distance moved by one oscillation times the number of oscillations. The distance traveled forward by one wavelength or by one oscillation times the number of oscillations or by times the number of wavelengths which are present. That is going to be the total distance. But remember, from distance equals to speed times time. The distance equals to the speed times time. And the time here was 1 second. So it means the distance moved per second is simply going to be lambda times f. But distance per second is the speed, remember? Because we got the number of oscillations per second times the distance moved by one oscillation, and the distance moved per second is equal to the speed. So V is equal to lambda f, and this is the expression you used in IGCSE, and you called it the general wave equation. So this is the fundamental wave equation, and it applies to all waves, whether electromagnetic or longitudinal. It is going to be applied to all waves, and it's going to be called the general wave equation. Remember that the frequency is equal to 1 over t, so I can also rewrite that equation in any form that I want. For example, V can be equal to lambda over t, because where there is f, I can put there 1 over t. So the wave speed, therefore, which we are going to call v, the wave speed is the speed at which a wavefront travels in the direction of propagation of the wave. The wave speed v is the speed at which a wavefront travels in the direction of propagation of the wave. That is the wave speed. Now, someone will say, why do we say in the direction? Is it a vector quantity? It is still wave speed. The speed at which a wavefront moves in the direction of propagation of the wave is what we call the wave speed. Of course, there is no possible way of the wave speed being in the opposite direction to the direction of propagation of the wave. So that's why we can just say it is the speed at which a wavefront travels. That is the wave speed. The speed at which a wavefront travels from the source is going to be the wave speed. So now that we know the general wave equation as speed equals to frequency times wavelength, or wavelength times frequency, then I think we qualify to try and use this general wave equation just to remind ourselves of the IGCSE concepts. The tuning fork of frequency 170 Hz produces sound waves of wavelength 2 meters. Calculate the wave speed. So this is the frequency, this is the wavelength lambda. So you just use V equals to lambda F and you substitute. Water waves of wavelength 0.08 meters, so this is lambda, have a frequency of 50 Hz, so this is F. Calculate the speed of water waves. I have to change this to green. So we know that speed V is equal to lambda times F. So I just substitute, since all of them are in SI units, 0.08 times 5. I'm very certain this is 0.4 meters per second. The speed of sound is 340 meters per second, so this is V. Calculate the wavelength of the sound wave produced by a violin when a note of frequency 500 Hz is played. So we want to find wavelength. So wavelength equals to V divided by frequency. So just divide 340 by 500 and you obtain the answer. And I think this is going to be correct. Sound is a mechanical wave that can be transmitted through a solid. Calculate the frequency of sound of wavelength 0.25 meters that travels through steel at a speed of 50-60 meters per second. So we want to find the frequency, so frequency is simply going to be V divided by wavelength. So they've given us the V as 50, 60 divided by V as 0.25. So I'll press my calculator. 60 divided by 0.25. So this becomes 20 to 40. 20 to 40, because this was frequency, so this is going to be hertz. A cell string vibrates with frequency of 64 hertz. Calculate the speed of the transverse wave on the string that their wavelength is 140 centimeters. So V is going to be equal to lambda times F, and this is going to be because wavelength frequency is in hertz, I'll change this to meters. 140 divided by 100, so this is 1.4 times 64. Always ensure that the units match. If they are both, if one is SI units, you can make the other to also be SI. So because frequency is in SI units, which is hertz, then the other one should also be in SI units. So this is approximately 89.6 meters per second as the speed. An oscillator is used to send waves along a stretched cord. 4 complete wave cycles fit on 20 centimeter length. So if I have 4 complete wave cycles on 20 centimeters, so it means one cycle, which will be the wavelength, is going to be 20 centimeters divided by 4. So the wavelength of one cycle is 5 centimeters. Okay. When the frequency of the oscillator is 30 Hertz. For this wave, calculate its wavelength. So we have seen the wavelength is lambda is equal to 5 centimeters. Its frequency, because the frequency of a wave depends on the source, the frequency is still going to be 30 Hertz. The frequency of a wave depends on the source. Its speed is going to be lambda times f, which is going to be 5 times 10 to the power of minus 2 to change it to meters, then times 30. So 5 exponent minus 2 times 30. So this is 1.5 meters per second. I want to just note the second part B. They gave us the frequency of the oscillator as 30 Hertz. And I've just mentioned that the frequency of a wave is the same as the frequency of the source. So since the source has a frequency of 30, then the wave should also have a frequency of 30. Determine the wavelength and amplitude of each of the waves shown below. So let me see wave A. Wave A is the one in blue. The wavelength is the wavelength is the distance between successive peaks from 15 up to 30. That is one cycle, I think. So wavelength is equal to 30 minus 15, which is 15 centimeters. Then amplitude is the maximum displacement from equilibrium position, which is going to be 4 centimeters. That is for A. Then for B, the B is the one in red. Wavelength is 20. Length for one cycle, the lambda is 20 centimeters. And then the amplitude for B is simply 2. That is basic. That is IGCSE. Copy and complete the table below. So we have radio A, radio B, radio C, radio D. All these are electromagnetic waves. And the speed V for electromagnetic waves is 3.0 times 10 to the power of 8 meters per second. So all your calculations should use this. So I'll just use lambda is equal to V over F to fill this. But remember, this is mega. So this should be times 10 to the power of 6. So I'm just pressing my calculator to find the wavelength. So for the first one, speed is 3 exponent 8 divided by 97.6 exponent 6. So this is 3.07. Then the other one is 3 exponent 8 divided by 94.6 exponent 6. So this is 3.17. Then here I will just make F the subject, and F is equal to V divided by wavelength. So just V is 3 exponent 8, and I divide this by 15. Remember, this is in mega. So I have to again, to bring a prefix, you divide by its value. So divide by exponent 6. So this is going to be 0.20 megahertz. Because this should be in mega, to remove you multiply by its value. To bring a prefix, you divide by its value. So then this one is going to be equal to 3 times 10 to the power of 8 divided by 693. But remember, I have to divide this by 10 to the power of 6 to change it to megahertz. So 3 exponent 8 divided by 693, then divide by exponent 6. So this is 0.43 megahertz. So that is here you're supposed to just press a calculator if you're very confident. So to sum up lesson 2, I want you to note the following. Number 1, we have mentioned that waves which transfer energy from one point, the most important factor is transferring energy from one point to another without transferring matter, are going to be called progressive waves. So we now know what progressive waves are. And of course, in progressive waves, the wave profile moves from the source to the surrounding region at the same speed as the wave motion itself. So the profile moves at the same speed as the wave motion. That's why we define wave speed as the speed at which the wavefront moves in a given direction. And also the vibrations of the particles are of the same amplitude and frequency, but the phase of vibrations changes from one point to another along the wave. Of course, we shall talk about how a phase changes with the time. So, but of course, there could be two particles which have the same phase, but from the two neighboring particles may not have the same phase, especially if a progressive wave. They have the same amplitude. That is very important because you need to compare progressive waves with stationary waves. All particles reach the same amplitude. But when you look at a wave, represented as a progressive wave like this particle here, A, and particle B are not in phase. However, particle A can have a corresponding particle somewhere on the other side which is in phase with it. So all the particles will always reach the same highest point. That's why we say they have the same amplitude. And of course, they will have the same frequency. In other words, they will move up and down at the same rate. But the phase of the vibrations changes from one point to another. So the two neighboring particles, A and B, are not in phase. However, we shall later on see for stationary waves that two neighboring particles are always in phase as long as they are between two nodes. As a class activity, you can try to visualize a progressive waves. You can attach a ribbon on a slinky spring and observe the position of the ribbon when the slinky waves are generated. Of course, this is an easy demonstration where you see that the ribbon just moves back and forth. In other words, it oscillates, but does not leave one end to the other end. However, you notice that as waves are being generated, energy is propagating from one end to another end, but the ribbon itself does not move from one point to another point. It just oscillates about the same position. That is a progressive wave. I think lesson 2 should end here. See you in lesson 3. Until next time, bye bye.